if you're following along in the playlist, then you just finished going through part 1 and part 2 of the counting example problem videos. Okay, in each part, the problems get a little bit harder. And so now, if you're comfortable working most of the problems in part 1 and part 2, then you've come a long way in terms of learning how to count. Okay, because with those problems, if you know how to work those problems, then you understand all of the different categories of counting methods, the permutations, combinations, how you work with repeated, non-repeated, indistinguishable elements within permutations and combinations, using just the pure sum rule, product rule, and then having all of these different counting methods mixed into the same problem. Okay, but now we're not done yet. There's part 3, part 4, maybe part 5 of counting example problems. So how are the problems going to get more difficult? Okay, well, going forward, what's mainly going to add more difficulty to the counting problems are cases where you have events with overlapping outcomes, right? So you're going to need to use the Venn diagrams that we discussed earlier in the playlist. Okay, and so before you start the full example problem videos, I wanted to go through an example here. And in this example, you can learn about derangements. So a derangement is a type of count where you have to make use of these Venn diagrams. It's like the principle of inclusion-exclusion. And so this is going to give you a sense of how you're going to need to apply the Venn diagrams to solve certain problems. Okay, so let's look at this example. 5 gentlemen attend a party, leaving their hats at the door. At the end of the party, they hastily grab hats on their way out. How many different ways could this happen so that none of the gentlemen leave with his own hat? Okay, so the idea is you've got these 3 or these 5 hats that are left at the door for a party. So you've got hat 1, hat 2, hat 3, hat 4, hat 5. Okay, and then at the end of the party, the gentlemen come to pick up their hats. So you've got gentleman 1, gentleman 2, gentleman 3, gentleman 4, gentleman 5. And so like gentleman 1, his hat is hat 1. Gentleman 2, his hat's hat 2, etc., right? And the question is, how many different outcomes are there to where no gentleman picks up his own hat? So what they're saying is, okay, one outcome would be, so you'd have gentleman 2, gentleman 3, gentleman 1, gentleman 5, gentleman 4. So gentleman 2 picks up hat 1. Gentleman 3 picks up hat 2. Gentleman 1 picks up hat 3. Right? That's one of these outcomes. Another would be gentleman 4, gentleman 1, gentleman 2, gentleman 5, gentleman 3. There's another outcome. Okay, and each one of these outcomes, in this case, are called derangements. We're trying to solve, in this problem, we're trying to solve for the total number of derangements. So what does that mean? What it means is that we've started off, you can think about how we started off coming in. We started off with this. Right? These were the guys' hats when they walked into the party. Gentleman 1 had hat 1, etc. And so what we're looking for is all of the outcomes where these are completely scrambled, where not one of these is on its original slot. That's the idea of derangements. Okay? And to solve a derangement problem, I mean, there's general formulas for derangements, but to either solve a derangement problem from scratch or to just come up with a general formula, you're using this principle of inclusion-exclusion, the whole Venn diagram idea. Okay, and so, but you could use the whole principle of inclusion-exclusion for all kinds of problems, not just derangements. Okay, and so, but the general way it's going to go is that you're going to have a problem, and it doesn't always have to go exactly this way, but this is the general way it works. You're going to have a problem like this. Okay, and then you're going to say, all right, well, I know how, using my just basic counting skills, I can get like a total count for this entire system, right? We can say that 5 factorial is all of the arrangements here, including where every guy has his own hat, including where one guy has his own hat, the others don't, whatever. 5 factorial is like the entire system, right? There's the entire system. It's 5 factorial. And what we're trying to do is we're trying to subtract out what we don't want. And so to do that, we're going to make sets that include everything we don't want. But these sets are going to be overlapping. If they weren't overlapping, then we probably wouldn't make a Venn diagram. We'd just go ahead and subtract them out. So we're going to, in general, have these sets that are overlapping, right? And we define these sets to where all of the sets taken together, which is, so if this is set A, B, C, D, all of the sets taken together, the number of elements, which is A union B union C union D, the number of elements, because this doesn't include duplicates, right? It's everything in A, everything in B, everything in C, everything in D, not including duplicates. That's what we want to figure out what it is. Because once we have that, then we could just come here and subtract it out, and we have our answer. Again, in general, this is how these inclusion-exclusion problems are going to work. It could be you could have special cases where you're trying to solve for other, maybe you're trying to solve for this intersection here or something, but in general, it's going to work like this. Okay, and so with that though, we know the formula for the union of the number of elements in the union of however many sets, right? We talked about that. We can write out the formula for A union B, union C, etc. for any number of sets, right? Okay. So what are, in this case, the system is all of the different possible orderings of any gentleman having any hat, right? Including their own hat. Now, if we're going to, so yeah, you can draw the Venn diagram, right? You might be thinking, okay, well, I need to draw the Venn diagram and see where the different overlapping regions are. But in actuality, you don't have to do that, and you probably don't want to do that. Instead, what you want to do is you just want to see, okay, how many different sets do I have as far as to encompass what I'm trying to subtract out, and then you just assume that they're all overlapping completely. And then you write out the formula, and as you're going through the formula, you'll figure out, okay, look, A intersection B intersection D, you'll analyze it, and you might say, okay, there's no overlap there, and you'll say it's 0, and that's how you'll account for no overlapping. You don't have to decide first and then not include it in the formula. Just write out the full formula to begin with. Assume they're overlapping everywhere, and then figure it out as you go. That's going to be the general process. So, okay, how many sets are we going to have within our system? To where we're thinking about the union of all these sets is what we want to subtract out. Okay, well, the sets are going to be based on a man having his own hat, right? So we could think about how you could, so one set could be any of the outcomes where gentleman 1 has his own hat. No matter what the outcomes are. It doesn't matter if other guys have their own hat as well. It doesn't matter. Another set could be where gentleman 2 has his own hat. 100%, every element in that set, gentleman 2 has his own hat. But whatever else, it doesn't matter. So we could have these 5 sets. And if we could figure out what is the number of elements in H1 union H2 union H3 union H4 union H5, if we can figure this out, then we have what we want. We just subtract that from here. Because remember, it's the total number of elements where gentleman 1 has his own hat, the total number of elements where gentleman 2 has his own hat, all those together, but no duplicates. That's the big key. It doesn't include the duplicates. That's what we want. Because this is all the cases where either gentleman 1 has his own hat, or gentleman 2, or gentleman 3, or gentleman 4, or gentleman 5. That's what we want. Okay, so we know the general formula for this is, so we start with, okay, what's the total number of elements in H1 plus the total number of elements in H2 plus, we start here. Okay, so what are the total number of cases where gentleman 1 has his own hat when they leave? They pick up their hats. The total number of cases where gentleman 1 has his own hat. So, okay, gentleman 1 comes here. That's there for sure. All right. Now, but these can be anything. We're left with, we can pick between gentlemen 2, 3, 4, and 5 in any order, whatever. So this is just 4 factorial. There's one outcome here times 4 factorial here, right? Because gentleman 1's not moving. We're not counting if gentleman 1 comes here. So no, it's just, so 1 times 4 factorial. But then this is going to be the same thing. It's all the same thing. You got 5, so it's 4 factorial plus 4 factorial plus 4 factorial. So we've got 5 times 4 factorial. Which is 5 factorial, actually, but I'll just leave it like that. Okay, now, what we do next is we subtract all of the different intersections of the pairings. So like H1 intersection H2, H1 intersection H3, H1 intersection H4, H1 intersection H5, then H2 intersection H3, H2, H4. So what's the total number we're going to have of these intersection pairings here? That's going to be, so we've got these 2 slots, because remember, the order doesn't matter with intersections and union. It doesn't H4, H1, or H1 intersection H4, it's the same thing. So it's, 5 choose 2. 5 choose 2. So it's, and that, so 5 factorial over 3 factorial times 2 factorial. So that's 5 times 4 over 2. So there's 10 of these. Okay. So let's think about what H1 intersection H2 is. So there's 10. Let me put 10. There's 10 of these. What's H1 intersection H2? That's all the cases where both gentleman 1 and gentleman 2 get their own hats. Right? These are fixed. This is fixed. Okay? So the count then is 3 factorial. There's one outcome here. We're not counting where these switch. No, G2 can't switch. So it's just 3 factorial, because you take gentlemen 3, 4, 5, you can put them wherever you want here. So 3 factorial, but then it's going to be the same result for all of these. So it's 10 times 3 factorial. So 10 times 3 factorial. Okay, now we add all of the intersecting triples, right? So we add, it's H1 intersection H2 intersection H3 plus H1 intersection H3 intersection H4 plus H1 intersection H2 intersection H5, etc. So, okay, but what's the total number of these going to be? It's 5 choose 3. So that's 5 factorial over, did I do that right? First, 5 choose 2 was 5 factorial over 3 factorial times 2 factorial. Okay, yeah, it's the same thing. So this is going to have 10 outcomes as well. All right. So what is, let's think about H1 intersection H2 intersection H3. That's gentleman 1 gets his own hat, gentleman 2, gentleman 3, 2 factorial, right? This is fixed. You have two slots left where order matters, 2 factorial. So, but this is still, it's going to be the same thing for all of these. So it's plus 10 times 2 factorial. 10 times 2 factorial. Okay, now we subtract all of the intersection of the groups of 4. So H1 intersection H2 intersection H3 intersection H4 minus H1 intersection H2 intersection H3 intersection H5, etc. So the total number here is going to be 5 choose 4, which is, it's 5 over, it's just 5. So, okay. Now we've got, so gentlemen, what's H1 intersection H2 intersection H3 intersection H4? So 3, it's 1. There's one case here. Is that right? Am I thinking about this right? Yeah. Just this here. Just this. There's only one case. But then we've got 5 of them, so it's, you add it up and you get 5. So we can write it like this. We can write it 5 times 1 factorial, so you can see like the pattern here. Okay, then we've got, we're left with, it's H1 intersection H2 intersection H3 intersection H4 intersection H5, and that's going to be, it's just 1 times 0 factorial is how you'll see the formula derived. But it's just 1. There's only one where they all have their own hats. There's only 1. Okay, and so let's see. 5 times 4 factorial minus 10 times 3 factorial plus 10 times 2 factorial minus, and then just 5 plus 1. So 76. So, okay, we want to subtract then 5 factorial minus 76. So 5 factorial minus 76 is 44. And there you go. So that's how, again, this was an example of a derangements problem, but this also illustrated the general way you're going to, for any given problem you're working, you might look at it and say, okay, to solve this, I can calculate the total number of elements in the system, and then I can create some sets and subtract out what I don't need, or maybe I have some information to where I have the sets that I define. I know what I need, or I know what's in those sets, but I'm trying to find some sort of an intersection. That gives you a general sense of how you're going to be using, solving problems that involve events with overlapping outcomes.